So as I said, today we are going to talk about modeling and simulation of processes for biomass conversion. Okay? But before we talk about simulation uh, and what is the importance of simulation, let me talk about revolution industrielle or industrial revolutions. I have a question for you. Anybody knows how many industrial revolutions we had in the past 3 centuries? Somebody can answer. And do you know what is industrial revolution? I'm sure you know. How many industrial revolutions we had since 3 centuries ago? Anybody knows what is industrial revolution?
Uh, One of them was inventing of stream of power and using the power stream for industrial purposes. I think another thing maybe is artificial intelligence. Maybe I'm not sure, but
You jump from the first to the fourth. There are two in between. Yes. So, okay. So, we have had 4 industrial revolutions. As Kazem said, the first industrial revolution, let me grab my pen. The first industrial revolution started in the 18th century, was when things started to be mechanized and using the energy of steam and weaving loom, these kind of things. Okay, so this is I guess, the first industrial revolution that almost everybody has in his mind. But we had in 19th century, we had a second industrial revolution that was related to mass production and assembly line, particularly because of the electrical energy. So because of that, things started to be more, easier. So production lines increased. After that revolution, we had third revolution in industry. That was mostly due to advances in electronics, especially generation of computers, okay, and internet. So that is a kind of revolution that started in the second half of 20th century. But right now we are in the era of fourth industrial revolution. As Kazem said, right now these days you see we are talking about digitization, digital area, and now things are not. Before, for example, you could say, okay, I studied chemical engineering. Somebody said I studied biology, chemistry, or whatever. Right now, there is not really a kind of border between fields. Fields are now really very integrated, and they are very related. And the most important thing that relates all these fields is really intelligent system, artificial intelligence, virtual reality, these kind of things that you have been hearing. Okay, so we are in the era that robots are going to decide for us. I mean, intelligence systems. So in opposite to industrial number two, for example, that things started to be mass production and hiring people, so people got a lot of jobs. They travel from villages to cities to do the business. Now we are at the era that computer, artificial intelligence, digitization, this kind of concepts that we hear these days are doing everything. Okay, so that's why you see that one of the top topics these days, they call it the science of 21st century is data science. We're in the era of data. Okay, so that why I talk about industrial revolution, because now we are going to talk about simulation. Simulation is really in the context of um, industrial fourth industrial revolution, because what you do by simulation is that in fact you are making a kind of hypothetical system, something like a virtual reality that you have heard of, where you can easily uh, predict what can happen. So you can transfer the reality, a real factory, and I mean translate it into computer language, okay, and then uh, by applying some changes into the system, predict what can happen, predict what kind of risk you could have in the process, what kind of performance you can obtain with your process. So this is really why you do simulation. Okay, so that's why right at the beginning I emphasize that for any chemical engineer you need to know an idea about simulation and a software programming, a programming software like MATLAB or C++, because um, you cannot just say I am a chemical engineer. No, a chemical engineer, a modern chemical engineer should be able to do simulation and you know uh, be able to quickly get an idea of the process efficiency or process complexity, whatever, uh, uh, without spending too much money. Because really, one of the big advantages of simulation is cost. If, for example, you are a chemical engineer, okay, and just somebody, and imagine you work at a consulting company, and somebody asks you, what do you think if I do this kind of reaction, I can make money if I commercialize my idea? I have an idea, I want to commercialize it. Do you think I can make money? As a chemical engineer, what you can say? You can say, okay, let me go to the lab, start experimental work, then do a lot of sophisticated things, and then build up a plant, pilot plant, or build up something, tell you what is the cost. Okay, of course, this is really wrong answer if you tell him that, if you tell such answer to that guy, because he wants you one answer in 1 week, not one answer after 5 years. So here is simulation. If you know how to do a simulation, of course there are uncertainties because you don't have experimental data, you don't have access to real equipment. However, you can do simulation by taking some assumptions, then you can identify what could be the performance of the process, and eventually, if that guy can make money by putting that idea into commercialization. Do you agree with me or not? I hope yes.
Yes, for sure.
So that's simulation. That's very important. Why? And so you save a lot of money. You save a lot of money. You don't ask the guy $10 million and then wait 5 years, blah blah blah. No, you say, okay, just give me $10,000. I'm gonna just buy license of Aspen. Just give me 1 week. I just want to spend some 1 week, and then I tell you what you can do with that. That's the beauty of simulation. Okay, that's why we are in the fourth industrial revolution. Things are going to be much faster. That's why data in 21st century is very, very important, because things are much faster and we are generating a lot of data. And in order to manage this data, we need to have um, simulations. We need to have artificial intelligence and many, many things that nowadays you hear. Okay, now after this very kind of deep introduction, let's talk about uh, our most, how can I get rid of this thing? Okay, let's now talk about our main topic, biomass conversion. So biomass conversion essentially is as you know, is the process, right? If you remember, last week I talked about onion model for process development. Anybody can tell me what was the onion model in process development? Onion model d'oignon.
Uh, Excellent, Professor. But I guess it is like a onion, and you must model your system layer by layer from simulating it as general and then going through details.
What are these layers?
Uh, maybe the first layer is simulating the mass balance, heat balance, and after that, we must going to model and simulate hydrodynamic instruments inside the reactors, distributors, and stuff like that.
But I'm not actually. I'm talking about the layers of process equipment. I have to clarify here when I'm saying um, onion model for process development. Here now we are talking. We are not talking about a procedure. We are talking about equipment actually. That, so I just wanted to clarify. What is the onion model in terms of equipment, design of equipment in any chemical process? You are right. We have different layers, but then so in each layer there are specific equipment. Okay, let me just uh,
We have
say
reactors
that
at the center, and next to that we have heat exchangers or separators,
exactly.
and
So
accessories like utilities.
exactly. So in the onion model of process design in terms of equipment is in fact four layers of reactors, separators, heat exchangers, and utilities. Okay, so when we talk about any process, the heart of the process is reactors. It means first you have to design your reactors. Okay, or I mean, you have to decide what type of reactor you need, what is the kinetics of reaction, what is the type of catalyst that you need, what is the type of en- enzyme that you need if it's a biological reactor, for example. What is the feed? What are the products? Whatever. So the first part of any process is really reactors. You need to first make sure that your reactors are clear. After reactors, the second is type of this equipment that you should design are separators, like distillations, like even filtration, leaching, extraction, um, condensation, any type of separators. Okay, that you should design. After you design reactors and then separators, what you have to what type of the equipment you have to design are heat exchangers. So mostly when we talk about heat exchangers, so you know there are different types of heat exchangers like shell and tube heat exchanger, double pipe heat exchangers, boilers, even condensers. But usually in terms of heat exchanger, in the third layer, we are talking about heat exchangers that the two streams that are exchanging the heat are process to process streams. There are two processes. There are two streams that belong to the main process. Okay. So to clarify more, the fourth layer of the process is about utilities. So utility in any chemical process usually is about electricity, water, and steam. Okay, so you know that, for example, We have heat exchangers in any process like the boilers. So inside the boilers, you have steam. Okay. So if you have steam, you can boil up water, for example. That boiler can be categorized in utility layer or condensers. In condenser, you use cold water, or in cooling towers, for example, you use cold water to cool down your material, your products. Okay, so when we talk about utilities, we are talking about usually steam, vapor, or steam, doesn't matter, which could be low pressure, high pressure, whatever, cooling water, and electricity. For example, if you have to use kind of electrical heater, so you need electricity. So you need to have a network of electricity around your company, or a network of water, a network of steam generation in the process. So you have to have an idea about your utility system. So talking about this onion model, um, if you want to layer by layer design everything from the core to the outer layers by constructing all these equipment, things are going to be expensive. So you can generate a kind of simulation interface, can do simulation and start simulating your reactor, and then start simulating your separators, simulating your heat exchangers, and simulating your utilities, okay, either in one place or separately, and then integrate everything. Eventually, you will have whole process simulation. Okay, so already we talk about simulation. So practically, uh, when we talk about simulation, uh, simulation is really a source of uh, uh, data that lets you, maintain a kind of heat balance, mass balance around your process. So, by in other words, by simulation, the very first thing that you do is to make sure the system, because as you know, in any chemical process or any process, doesn't matter, mineral, pharmaceutical, electronics, even whatever, heat balance, and mass balance are very important. So you know that when we say balance, we are saying always input minus output plus consumption. Okay, okay, should be equal to accumulation. Okay, this is the. It means if you have input and you have output, but inside the reactor you have also some chemical reactions, so some consumptions. The total of these values should be equivalent to accumulation. So you know that in a steady state processes, usually accumulation is zero. So in general, when we say balance, either in terms of energy or in terms of mass or material, is that input and output should be consistent. It's like you earn $20, but you spend um, $19. Okay, so what is your saving? Your saving or is like $1. Okay, it's really the mass balance in terms of your money, your expenses. The same thing for in chemical processes. So the very first thing that you do with simulation, I'm emphasizing because honestly, even some very advanced people, they really don't know why they need simulation. So the very first thing that you do simulation is to make sure that your process is balanced in terms of energy and material. Of course, the second objective of simulation, and in my opinion, the most important objective, is computer aid is uh, computation aided process design. You do process design assisted by a computer. Okay, that's the most important advantage of simulation. As I said before, you don't spend too much money. and you don't want to waste a lot of time. You do right away a very preliminary simulation to give the best answer. But of course, by doing simulation, you can analyze your process and identify at what part of the process you have issues, you have challenges, you have inefficiencies, and in other words, let's say you have a process and your boss tells you, what do you think if, for example, that specific stream, instead of going to unit number one, should go to unit number two, and then from unit number two should be back to unit number one? What do you think? Do you think the process could be more efficient in terms of energy saving, for example? The best answer is to do simulation. So you maintain a simulation, you just change your streams, change the equipment, run your simulation and see the result. And then you can answer your boss if his idea works or not. Okay. So already I talked about this slide. I don't want to go to that detail. So you do simulation either for a factory that exists within existence. It means a factory that exists. Okay. So to do the simulation, you need some tools for such kind of things. The very first tool that you need to do a simulation for a kind of existing process is to have uh, process diagrams. Okay, anybody can tell me what type of process diagrams we have? Like block flow diagram, like other diagrams. Anybody can answer?
You can have a PFD and PNIDs,
What is PFD
process flow diagram.
and what is PNID?
It's more detailed process flow with instrumentation, so with all
Yeah, so
captors and control systems.
exactly. So P and ID. P means piping. ID means, as you said, instrumentation. D and D stands for diagram. Exactly. So we have block flow diagram, which is very general, that just shows the layout. Consequence of the equipment. Sequence of the equipment. But process flow diagram is the diagram that shows you uh, what type of process equipment you have in your factory, okay, and what type of um, kind of streams you have. So process flow diagram is the most important diagram that you need in term to check mass balance and heat balance of the process. But PNID is more advanced diagram that gives you information about size of the pipes, because in any, that in any company, in any processing company, transportation, most of the transportation are through the pipes. Okay, you have conveyors, you have other things, but most pipes are very important in mostly in chemical processes. So what type of pipe is the 20 inch, 40 inch, 2 inch? What type of pipe? Because all these data are important to know if you want to do much more advanced uh, simulation. And instrumentation. Why instrumentation? Because in any chemical process, okay, usually you have um, you have some important parameters that you have to control, like temperature, pressure, flow rate, um, and much more. You know, and you need to identify the tools that you need, okay, to control your process. Let's say you have a reactor that operates is exothermic process, and since it is exothermic, you have to keep the temperature at 300 Celsius. And if the temperature goes beyond 350 Celsius, Since it is exothermic, accidents can happen. So by chance, the temperature can go to 350 Celsius. If that happens, maybe you will have explosion, or maybe you burn or you damage some of the internal material in terms of mechanical parts inside your reactor. So always you need to have a heat exchanger inside the reactor to keep the temperature at 300 Celsius. So to make sure that temperature is always at 300 Celsius, you need to have a controller. You need to have a thermocouple. The thermocouple is connected to a control room that always records the temperature inside the reactor. Okay, so information about temperature control, these kind of things, the diagram of the process control are available in PNID. So you need anyway, you need a PFD or PNID for simulation. By knowing these kind of diagrams and also by talking to other people around the factory, you do data collection. Collecte de données or data collection. You need to collect all data that you need, and then based on data that you collect and the diagrams that you have obtained, you construct your simulation. Okay, depending on the software that you use. But once after you do simulation, you have to do reconciliation. You have to do the reconciliation of the data. Why? Because again, let's say for example, let me draw something here. Let's say, for example, uh, flow rate of water. Let's say flow rate of water, you always want to keep it at 100 kilogram per hour. Okay, so this is uh, always versus time. So always you want to keep the water flow rate at around this flow rate, 100 kilogram per hour. But uh, Um, So you have as I said, you have the control system, so always records your data. So you see that all data that you have are around the set point that you are expecting. But sometimes some data are really shoot, they are really far from the set point. Okay, so here you have to do reconciliation. You have to really, work on your data to make sure that so reconciliation itself is a special procedure. Either you remove your error, your data that you think they are error, or you just take average of all data that you have collected. So there are different things that you do for reconciliation of data. Okay, after you do reconciliation of the data of experimental data that you have, or real data that you have recorded from the plant. You compare this data, reconciliation data, with simulation data, okay, in order to validate your simulation, okay, because once you do simulation, how can you confirm that your simulation is acceptable, is right? Okay. If we are talking about the existing plan, we are not talking about a plan that doesn't exist. So when you have existing plans, you have recorded all data. So you have to compare your simulation data with the recorded data. Okay, in order to do validation. So then validation means that comparing between simulation and uh, reconciliated data. Once they are inconsistent, you are okay with that, so you accept your simulation data. So once you have the validation, then you use simulation for other uh, objectives. For example, now you have developed a very reliable simulation interface. So you know that your simulation is right. It is consistent with experimental data or factory data that you have recorded. Now you can easily play with the configurations. If you want to change the streams, if you want to change equipment of the process. If you want to, really challenge the process to make improvements or to identify problems of the process, you can use that simulation for other purposes. But if you have a factory or a plant that just new, okay, for this kind of plant, again, so you know that when a plant is going to be constructed, usually we have two types of engineering work. We say basic engineering design and detailed engineering design. Okay, so when we are talking about the new unit for basic engineering design, usually we have to generate some again process flow diagrams based on uh, some, let's say, research and development activities, or some literature review, or some estimation that you have made. You generate the kind of process flow diagram, again, PFD, PNID, or whatever. Okay. Based on those diagrams that you have generated, you collect design data, and then you do your simulation. You construct your simulation, and then you validate. But validation here is not the same as validation for existing plant. The validation here is how? When you have a new process. The validation here is a bit challenging because it is based on the basic engineering data. So if you remember here, we talked about the design data. Sometimes these design data are based on lab scale data, so are not very uh, uh, I can say reliable for larger scale. At the end of the course, we are going to touch that part at this point. But anyway, the best kind of validation that you can do here is just to validate your simulation data with your whatever you have from your basic engineering stage, and you have to make some decisions if you see that there's a huge kind of difference. You have to make some decisions that we are going to talk at the end of the course today. Anyway, once you validate your simulation, you use it for other purposes. So already I talked about these slides about how to do uh, simulations. So as you see, for example, here uh, in this slide, so you use, for example, PNID for a special network of water consumption in a system, and then you use a simulation. By doing the simulation, you end up with the kind of improved design of the water consumption. For example, this is just an example. Another thing in terms of simulation is that simulation can be either a steady state, in French we say régime permanent, a steady state simulation, or uh, dynamic simulation. Okay, what is what is a steady state simulation? What is dynamic simulation? This could be a question. Usually, when we design, usually when we start the simulation, we assume that everything is perfect in the process. We are not going to have any error. We are not going to have any accident. We are not going to have any malfunction of equipment. For example, flow rate of the water, for example, is always at a specific value of 100 kilogram per hour. Blah blah blah. So you always assume that all the data that you use are fixed versus time. Okay, there is no variation. There is no oscillation of data recording. So you do simulation based upon with this assumption in order to do many things like we discussed before, for economy evaluation, for identification of instabilities, errors, for making improvement, whatever. But in reality, this is actually, as Celia said, is good, is right. But in reality, if you want to do a very good and advanced simulation, you should also consider dynamic simulation. So when we say dynamic simulation, it means always uh, uh, you have accidents, you have errors, you have variation of the parameters versus time as let me just plot it here. For example, as I said, you have always data that you record are always like this versus time. If for example you want to measure temperature versus time, you have always oscillation of the data. Nothing is fixed. It is for many different reasons. For example, pump when pump pumps a fluid to a pipe, because of the function of the pipe, okay, because it's pushing, uh, you cannot always say that the flow rate that you record is always constant. It depends on at what stage of the pumping you recorded. So always, as we have presented in this diagram, always process parameters vary versus time. Okay, so we have to do a simulation uh, to always consider this kind of the dynamic behavior of the process. Why? Because if something happens to the process, what can you do? Let's say uh, pressure, right? For example, pressure of the reactor goes beyond the set point, goes beyond the safety level. What can you do? Okay. If, for example, temperature goes beyond what you need. If the flow rate, if the flow rate drops, let's say you are feeding biomass to a reactor, and let's say it's a gasification reactor. It operates at 800 Celsius. But for some reasons, since we are talking about biomass materials, they are solid, right? They could be plugged inside the pipe for some reasons, because of the moisture, for example, maybe, and the biomass doesn't go into the reactor, just plugs. Okay, so you have no feed to the reactor, so the feeding rate is zero. What happens to process? What happens to reactor? So these kind of incidents that can happen are the matters of dynamic simulation. So if something happens, the process knows what then you can do. That's the advantage of dynamic simulation. Okay, I want to pass these slides because they are just easy. We talk about them more about data collection, data reconciliation. Talking about the simulation itself. First, we talk about diagram du procédé de référence, process flow diagrams. So you know that there are software like AutoCAD and Microsoft Visio and um, SolidWorks. So there are different softwares that you can use for drawing your process flow sheets. So, uh, personally, if you ask me, beside simulation software and programming language, another software that any chemical engineer should know is a software for drawing. Most traditionally, we think that drawing should be done by a mechanical engineer or a civil engineer, whatever. No, AutoCAD, Microsoft Visio, they are extremely important. You should know it, and they are very easy. And actually, they are very fun. You can easily learn them. So, okay. So now let's a bit talk about some uh, uh, information that you can obtain by a simulation. So imagine this process, which is about a craft lignin process. Okay. By the way, our next biomass cafe is about the craft lignin process. Please, because I don't want to remind you the one day before biomass cafe. So you go to Plan de Cours and you see when is our next biomass cafe? I want you all groups, to really go and study the process of craft lignin, and to really understand what is the process about and how it works. You know, what are the different steps inside craft lignin, because this is one of the very famous and popular processes in pulp and paper industry, in cellulosic industry. Okay, so the next biomass cafe, you are supposed to, you know, provide your insights into this process. But today, I want to go through the process quickly. So uh, the main part of the process is here. Okay, so in the process, you have wood chips. Wood chips, they go to the delignification step, and then there's a washing step, bleaching step, drying. Okay, after drying, the pulp is produced. But at the washing step, you have two phases. Okay, a liquid phase and solid phase. So the solid phase here goes to concentration. After concentration, you have boiler recovery, and after you have reclassification, launching, and that's it. But the product from the reclassification is back to uh, delignification step. Okay, so you see that in this process you have different stages, and each stage includes a couple of unit operations: reactor, separator, filter, heat exchanger, whatever. And you see that around the main process, you have also utility. You have flue gas, you have water. So this is the flue gas that produced in the process, but you have also purchased fuel uh, for the energy supply. And on the other hand, also you have water consumption, and you have some condensates that are produced in the process. So you can see that around the core of the process, you have utilities. So if you want to run a simulation of the process, there are different ways. Uh, but the the best way to do simulation is to do a progressive simulation. What does it mean? Uh, Progressive, it means, for example, let's say you have different stages in the process, or different unit operation in the process. Let's say block 1, block 2, block 3, block 4. Okay, so you can do simulation by considering all of these, for example, 4 blocks into your simulation interface, and then run simulation, and then bingo. Okay, it is possible. Some softwares, they can handle this kind of simulation, but the challenge is that the calculation time can be high, and convergence also can be sometimes not easy. Convergence of the calculation, because simulation is a kind of mathematical work. So always simulation should make sure that the error of the calculation are minimum at a specific value. Okay, so but successive way or progressive way is that, for example, first you simulate block 1. So in block 1, for example, you say you have one inlet. You have one inlet, and you have one also inlet from here. Okay, um, which is a kind of return stream from block 3. But by the way, you simulate block 1 first. Okay, to obtain information about the exit stream, which is the feed of the block 2. So you simulate block 1, and after it's done, you consider block 2. You just put it into the let's say this is the reactor, this is a kind of separators, whatever, so you consider block 2, and then you do simulation until, so one by one you do simulation until everything is well simulated. But you know, there is one specific thing that you need to know. It's good that you know it. Is the problem of loops or return streams. You know, in chemical industry, it's very common that some streams they they return back to the initial stage of the process. For example, as an example, in this process, in the craft lignin process, you see that one stream here is returned to delignification stage. So this is always a common thing in simulation. Okay, so how the simulation can work? There are different ways. You know, imagine that, for example, you have in this slide, you have M1 and block M2 with four streams of C1, C2, C3, and C4. C4 is a stream that returns from block M2 to block M1. Okay, so how simulation works is that, for example, as shown here, you can cut the stream here from a simulation point of view. You can cut the stream here, okay, and you know, just consider block C1, okay, just consider block C1, okay, uh, by making some assumption for this return stream. By making some assumption for this, you can guess, you can consider if it is fluoride, for example, you can consider the value is 0. You can make an assumption, whatever. Okay, you do simulation, but then also once you want to simulate block 2, you do since after simulation of block M1, you have information about the stream C2. You start simulation of block M2, okay. By doing this simulation, you get a new value information about the flow rate of C4. Okay. Uh, okay. So if you have the value of C4, let's say based on the simulation, individual simulation of M2, you get a value of 10. And then simulation will compare this new value with the initial value that you had, the value of 0, for example, that you had considered, you had assumed for simulation of N1. Okay, so if the simulation sees that the values are not consistent, simulation will take the value that you got from M2, I mean this value, for another simulation of N1. Okay, so again, by taking the value of 10, for example, simulation of M1 will be carried out. So subsequently, the simulation of M2 will be carried out, and again, a new value of C4 will be generated. Let's say that the new value of C4 is going to be like 10.5 after the second iteration. So based on the criteria that you define into your simulation software, based on the criteria, if, for example, you say 10.5 minus 10 divided by 10, 10.5 is a very low value, is like a less than 5%, you can accept the value. So you can say, okay, 10.5 is the real value of C4. So this is the way, this kind of iterative calculation of the loop stream is the way that simulation softwares work. So in this slide, a formula is given here. So you see that, for example, this epsilon is the criteria for the iteration. Once the value, for example, of the iteration number n minus the value uh, of the previous iteration divided by the new value of the iteration is below epsilon, you accept you put software assumes that the convergence is okay, and then it stops. It goes to the next calculation. This diagram it just shows you how iteration works. For example, for this case, for the stream number 4. Here in this diagram, shown for W4. I don't know why they use this graph like that, not C4. By the way, let's say you want to get the follow rate of W4. So you can see that the simulation has done 50 iterations, okay, to minimize the error. You see the error at certain point was, for example, 1%, and now this is even much, it's like a 0.001, less than 1%, 0.1%. So, so you see that the you reach to the value that you accept the error, and then the convergence is okay. By the way, when you do simulation, sometimes we do simulation not only with one specific software. Sometimes you use spreadsheets or some other simulation softwares, so that you, for example, uh, you have raw data, or you have raw data from your company. You get information from data, but they are not still ready for simulation. Once you learn, for example, how Aspen Plus works, you can see that data in Aspen Plus is a software that is developed for specific purposes and a specific way of calculation. So you need to play with data in order to make them understandable for Aspen Plus. For example, let's say for example you have um, uh, just a very simple example. Let's say you have a software that is that accepts temperature in the with the unit of Celsius, but your data from the plant are based on Fahrenheit. So but the software doesn't understand Fahrenheit. So you have to do just simple calculation Excel to convert all the temperature data from Fahrenheit to Celsius, and then import that data from Excel to simulation software. And also, it is also very practical that after you get information from software, you use the simulation data, you export the data from simulation to another software, for example, another spreadsheet, in order for further analysis of data. Let's say, for example, you want to do technical and economic analysis, but you don't know how to do it with the software, or you don't trust software. But you use the software just to give you simulation data in terms of temperature, flow rate, type of the equipment, blah, blah, blah. But you use this, you make your own spreadsheet for sizing of equipment and of eventually cost calculations. Okay. About the validation of simulation, already we discussed. I want to pass these slides. Already we discussed them. Just some examples on importance of simulation. In this slide, okay, in this slide, uh, consumption of water in different stages of craft lignin is shown. Okay, based on based on simulation data and the plant data. Okay, so mill is the refractory in the pulp and paper. So you can see that based on the simulation, most of the simulation data and actual data that were recorded are consistent. However, in some cases, you see that based on simulation, there is a big difference between simulation data and actual data. So this is actually one advantage of simulation. So you did simulation, since already, it is important, since already you had validated your simulation, as we discussed before, now you can trust this data, because you have validated that your simulation is reliable. So after that, you are using the simulation for example, identification of issues of the process. So now by looking at this data, you trust your simulation. So you believe that, okay, so it looks like simulation tells me, for example, water consumption uh, around the caustic effluents should be at this value, but the water consumption in real data was low. So then you doubt what happened, why it is low. So by looking at this simulation, you identify that there is something wrong in data recording. So you call your engineers or your operation engineers to go to plant and make sure what's happening, why simulation and real data are not similar. Okay, similarity for other parts of the process. For example, this graph shows uh, uh, compares simulation data and actual data in the steam network of the craft process. Again, you can see that in some units of the process, simulation and actual data are not very close. Again, you have by since already you have it's very important. Please pay attention because this is really a case. Some people forget this very delicate thing that I'm telling you now. I mean, I have been telling you. When you do simulation, you cannot right away go and run a simulation and compare simulation data with actual data. Before this comparison, you have to do a validation, as I discussed before. You have to validate that your simulation works. Believe me, this is something that many people ignore and it's wrong. After you do validation, you do the comparison, then now you can, by looking at this kind of information, you understand, okay, the process, there is something wrong in the process. Let's see what's happening. For example, it is about the steam. Maybe, maybe the boiler is not functioning properly. Maybe something else is happening. Maybe, for example, there is something wrong with the flow rate of water. That's it. So, beside identification of like issues, inefficiency of the process, or another advantage of simulation is that you can have an idea of distribution of let's say, for example, material in the plant. For example, in this pie diagram, you can see how much water consumption is distributed across the plant. For example, you can see here that um, water consumption 22.5% in drying stage is the maximum. Okay, and in evaporation also you have high water consumption. Sorry, vapor. I was wrong. Vapor consumption. Okay, of course in drawing you don't have what is because vapor. In this pie diagram, you see uh, production of the condensates. In the graphite, condensates are produced, so you can have an idea where maximum condensates are produced. Based on this, we can see that in recovery stages, and in the vapor injection, you have the maximum condensates. So you see, by doing simulation, you get a lot of statistical information about distribution of the utility. For example, in this case, water and vapor, condensates and vapor. You get a good idea about utility distribution across your plant because it is extremely important that when you do process, any process is always economic, is always technically viable, also environmentally okay. So if, for example, talking about effluents or waste material in the process, if you have uh, a lot of waste material production in your simulation plant, in your real plant, You might have issues with environmental risks. So by doing simulation, you identify at what stage of the process the maximum waste is produced. Then you make policies in order to minimize it. So these are other two the pie diagrams that show water consumption and distribution of effluents in craft lignin process. For example, since we talk about distribution effluents, I mean the outlet streams, you can see that, for example, in bleaching stage, you have the maximum production of effluents. So bleaching craft lignin is the one stage that has to be specifically considered in order to manage environmental risk, for example. And these are some other examples. For example, here in this specific case, you do simulation. Uh, Actually, this slide is about a modification that you can do on your process just by simulation. You have done a simulation, for example, for this part of the uh, craft process, bleaching unit, and you identified that by having water in at the inlet temperatures of 47 or 69, you need to have 45 ton per day consumption of steam in order to generate the pulp. But by playing with your simulation environment and by you know using your creative tools and by your engineering knowledge, you can end up with some simple, you know, uh, improvements. For example, by just uh, increasing water temperature to 57 and 79, you see that the flow rate of the steam has decreased from 45 to 38 ton per day. So it's a huge, not huge, but considerable reduction of the steam production. So, of course, you might tell us, okay, what is the trade-off here? So, of course, after this kind of simulation, you should also do techno-economy calculation or evaluations to see if it is worth it or not to increase the water temperature in favor of lowering the mass flow rate of steam. So, just what time is it? So, talking about simulation, I can give you 5 minutes break. I know simulation is a big topic. I can give you a 2 minute, just 5 minutes break. I will continue at 2:05. Okay, it's 2 o'clock almost. Uh, we continue the process uh, at 2:05. I just want to make sure that you can follow the process. Any questions so far? Okay, let's continue. So let me share my screen again. Uh, Before I continue rest of the course, I want to talk about the Moodle. So section 7 inside the Moodle is about this chapter. So presentation is here, but also I have put two references that we are going to discuss it now. I extremely uh, strongly I recommend that you go through especially this article and similar articles on simulation of biorefinery processes. This one is about bioethanol production from a hardwood, but there are many other simulation work that they give you a lot of help to understand how to develop your project actually. But also we have put three references for Aspen Plus in order to get familiar with more details of Aspen. But as I said before, I really think that this book is really good. That is really good book, and it can really help you to easily understand how Aspen works. So basically, now we would like to talk about Aspen. There is the last part of the course. I don't think I can finish today, but I will talk about it maybe just next first half an hour of the next Tuesday. So in terms of process simulation, you know, as this is always I have issue with this. So in terms of simulation, there are different softwares that we discussed. There are some simulation softwares like CADSim Plus or WinGames that are specific for pulp and paper, but there are some more inclusive uh, softwares like Aspen Plus, HiSys, Poro 2, and some others that exist. Okay, so Aspen Plus is one of the most important softwares. Not, I'm not advertising software because it's not my product, but as a tool, it is very important, very good simulator because it is still it has some limitations, but it includes many things in terms of equipment, uh, property package, in terms of material. For example, some softwares they are not good for simulating solid material, solid part. Uh, they are mostly for gas and liquid systems. But Aspen has the strength of understanding what is a solid. You know, this is one advantage of Aspen. There are some studies here, but I will go to Aspen itself directly. Before, let me talk about something very important. So, any simulation, uh, any simulation is based on some specific input. Okay, which, for example, what type of material you have and what type of kind of energy you are going to use in the system. But beside material and energy information in your equipment, in your simulation, in my opinion, the most important um, input information that you should provide to your simulator is the thermodynamic method, or in other words, your in Aspen they say property package. Why? Because as you know, I'm sure all of you have passed thermodynamic course. In other words, if you haven't studied thermodynamics before, I strongly believe you should go and study thermodynamics, or even if you have studied and you have forgotten, you really need to know uh, uh, principles of thermodynamics, especially the, those sections about phase diagrams, equilibrium information, and this kind of things. Because simulators are heavily dependent on thermodynamic packages that you use. As you see, for example, in Aspen, you can have um, physical property models based on four types of thermodynamic methods that you can choose: ideal, equations of a state, activity coefficient models, and special models that are developed for specific cases. When we say physical property models, okay, what are these physical properties? Okay, one of them is, of course, heat capacity. Heat capacity, CP, is very important because all the energy calculations are based on CP. Okay, another one is viscosity. You know, when you want to pump a fluid from one point to another point, you know that pressure drop of the pipe, for example, is a function of viscosity of the fluid, right? So viscosity, how software can calculate the viscosity, how software can calculate heat capacity. Another physical properties like electrical conductivity, thermal conductivity, you know, these are physical properties that software requires. So software should calculate in order to give you simulation data. But these physical properties are heavily dependent on the type of the thermodynamic package that you define in Aspen or any other software. Okay, and there are many thermodynamic packages, and it's really selection of the right thermodynamic package is really a function of your expertise, how much you're familiar with simulation, and also how much you're familiar with your own process. If it is biomass, even in terms of biomass, is it a thermal process? Is it a biological process? Is it a chemical process? What type of process? Is it a gas liquid or uh, gas liquid solid, or is it liquid solid system? Everything is really something that requires your experience. But if you don't have experience, the best tool is to talk to people who have more experience than you, or a literature review, books, articles, patents, reports, whatever that you can find, everything that help you to understand the process in order to find the right thermodynamic package. Because if you don't find the right thermodynamic package, your calculations really could be wrong. Okay, so here just two classes of thermodynamic packages are mentioned: equation of state like Penn-Robinson and Redlich-Cohen-Swall, and models based on activity coefficients. I hope that you guys know, and I really want you to know at least what is the difference between equation of state or equation d'état or equation of state and models based on activity coefficients like NRTL, Unifac, Uniquark, and Wilson. So you know that if, for example, if you are in oil and gas, in conventional oil and gas systems, Penn-Robinson or Redlich-Cohen-Swab are most popular thermodynamic packages. But if you are dealing with the seed process where liquid phase is very important, and where liquid phase is very important, and especially um, your system is not the ideal system, and you have a specific dilution, for example, This is where you need to really understand what kind of thermodynamic package you have to use. Okay. Uh, Regarding biomass, uh, Aspen essentially was developed for oil and gas industry, but now Aspen is more robust. It includes several industries. But fortunately, since 1996, so people who work at NREL, they developed a library for Aspen so that Aspen now can identify some biomass components. Because it is really a challenge to define a component in simulation. As I said before, in simulation, simulation really depends on the input information. One of the most important input information are material or components. So what type of components you have in your process? Sometimes we don't really know what is the component. Okay, so for example, for crude oil, we don't have, or for biomass, biomass has a lot of formulations. So it's really a challenge to define biomass accurately into Aspen. But at least some efforts already have been done by people at NREL to define these kind of components into Aspen. You know, but if your biomass doesn't have these components, or it has components beside or this component listed in this table, you have to do literature review, and then you have to find ways to introduce them to Aspen. So that's why I am again emphasizing this book, because this book really tells you how you can define components into Aspen if they are not conventional components of Aspen. Okay, so there is, as I said, this slide and the next slides are about a process for production of bioethanol from biomass. Okay, I don't want to go through these slides because they are fairly easy. You can really understand. So it's just about identifying different sections of the process: pre-treatment, detoxification, conditioning, fermentation, and separation. As I showed you in the model, this article already exists in the model. I want you to really go and study this article. You will easily understand this process, because um, it otherwise I have to spend one day to explain, to go with you to explain details of the simulation. But you can follow the slides and see what type of assumptions are made. But what is I want to really emphasize uh, here, since especially in biomass conversion, ethanol production is one of the top topics. I want to just emphasize on uh, the separation point in biomass conversion. You know that in thermodynamics, when you have two mixtures, let's say two liquids, and you boil them up, okay, the one that is more volatile will evaporate faster than the other, and that's why, and you end up with this kind of phase diagram um, uh, in terms of boiling, for example, a mixture of two liquids. But for some specific liquids, like the case of ethanol and water, you end up with the point where concentration of the vapor phase and liquid phase is similar, and we call it azotrope point. Okay, this is extremely important. It means that if you want to separate water from alcohol in order to enrich concentration of alcohol, you cannot operate your system around the isotropy point. Okay, you have to always operate at at temperature close to isotropy, so you can have this kind of separation. Okay, I'm emphasizing it because I want you to really go to your thermodynamic course and really study isotropy point, because this is the question that could be a matter of your TD and exam. This is very important, isotropy point um, in separation of alcohol from water. Okay, so but beside that, what I want to say is that in back to this process that I left it you to study. Once when you face with this situation that you have to do distillation, but you have isotropic, you don't have you don't have the chance to separate alcohol, for example, from water completely. Okay, so you have two ways. One way is to have a fractional distillation, for example. So you do a distillation first, and then the mixture goes to a second distillation. So by this kind of fractional distillation, you recover all the alcohol from water. But in this specific case, for example, you see they use molecular or molecular sieves. So they use one simulation, but after that, the mixture of water and alcohol goes to a molecular sieve, okay, to absorb the water, and then alcohol will be free. So I just wanted to emphasize about importance of simulation. By simulation, when you do simulation, you can easily understand. I mean, simulation itself can tell you that at this specific point you have isotropic point. You can have isotropic situation. So, by since you have distillation, you have software in front of you, you don't need to go to lab and practice experimentally fractional distillation. You can either do a fractional distillation inside simulation software, or distillation plus other types of separation, including molecular sieve. Okay, so this is about simulation. As I said before, when you do simulation, it is very common that sometimes you have one main simulation software like Aspen, but you can have other softwares like Excel and CATSIM Plus, for example, in order to get some information from one software and import it to other one, and then export the information from that one to the first one. And by this kind of loop, you want to really make sure that you have very strong simulation job. So there is one section about process scale up. I leave it to Tuesday because otherwise the message cannot be complete today. I just want to go to Aspen itself. So do you see my? Can you confirm that you see my screen?
Yes.
Yes.
Okay. So talking about Aspen, let me. I just want to give you a uh, very quick introduction to Aspen itself. By the way, since you are all students of Polytechnic, you have free access to Aspen. Ariane, I think she sent you an email that how you can have access to Aspen from home, because otherwise you cannot use Aspen. So to click to file and then new. Okay. See, Aspen already. This is the advantage of Aspen. Already has uh, categorized simulation environment depending on your process. If it is air separation, chemical process, electrolytes, gas processing, metallurgy, pharmaceutical, polymers, refineries, solids, or any environment that you would like to manipulate for your own. Okay, so let's say I select chemical processes. You select If you select chemical process, it provides you some options, either English unit or metric unit. And if it is about the specialty chemicals, why Aspen has all these options? If you remember, I told you in simulation, selection of the thermodynamic package is one of the most important things. So once you select uh, the specific industry or the specific type of process, Aspen already uh, selects a couple of thermodynamics that are more relevant to that type of process that you like. So it helps you to better and quicker select your process. If you are not sure what kind of equipment, what kind of process you have, you can just select blank and recent, or just blank, you know. So it's a common, but then it's difficult for you to select what you want. But anyway, let me just select blank. If you so let me close the previous one. So always we see this kind of message. Okay, okay. But once Aspen starts, you see you have two menus, one menu here and one menu here. So the upper menu is in fact depends on the selection here. So when you if you click on properties, you have this kind of information here. But if you click on simulation, you know it see information here and folders are different because here you see all the information about the simulation things. But when you want to start Aspen, first you have to click on properties menu. So you start here. You know, if you see in the properties menu, you have some options: setup, components, methods, chemistry, properties, data, and so on and so forth. If you click on setup, it is just about specification. If you want to give a title to simulation, if you want to change the unit of your simulation, English unit, metric unit, SI unit, whatever, you know, here you can, for calculation options, um, if if you want to, uh, specify some calculation reports, for example, you do everything here. So it's about calculation, flash convergence. You remember I talked to you about convergence? Here we have tolerance, for example. You know, these values are really, really important. That so as you see, for example, extrapolation threshold for equation of a state zero point 0.1. These values here are important values that you put you decide for software in order to converge simulation. But if you are not sure what data you need, you can just keep predefined values of the software. System, you limits, the reactions, whatever. So you can put information here. But after you set up your simulation, okay, the important thing, as I said, is components. Okay, if you click on component, the menu here starts. Let me here I say, for example, lignin. Okay, as I told you, lignin is now identified by Aspen. Previously, it was not identified. You had to define lignin. But once you select a component like a lignin, you see in front of the lignin, it says conventional. It means that Aspen understands lignin, and Aspen already assumes heat capacity and viscosity and other physical properties of lignin, and he knows how to calculate them under different temperatures and pressures. But you can, if you have a specific lignin or you are not sure what type of lignin, or you don't trust the lignin that is defined in Aspen, you can, you know, uh, you can uh, change the conventional to other type of selections and make some changes to the definition of the component. For example, you can say hypothetical liquid. It is a liquid just defined as hypothetical liquid, but then you have to go and define to specify what you mean by this definition. Or you can just say that it is a non-conventional lignin. It means that you cannot, Aspen cannot do all calculations based on predefined physical properties of lignin. You need yourself, you need to go and make some arrangements. So you see, anyway, when you say component, there are several options in order to specify your component into uh, Aspen. So it's about lignin. Let's say, for example, I say steam. See, if it understands the material tells you conventional. But let's say, for example, I say biomass. Okay, so see, biomass is defined by Aspen, but we know that biomass is a very general word. Hardwood, softwood, I, sorry, rice straw, wheat straw. There are tens of thousands of biomass material. You cannot use just one biomass in your simulation. You really need to define what type of biomass you are using. That's why I'm emphasizing in this configuration. However, you can go to the library of Aspen and see what type of biomass is defined. If it is similar to biomass that you have, it's okay. If not, you need to do some changes. Okay, so it's about components, but about the methods. About the methods, again, it's about physical properties. So you can make a filter if when comment is selected, it means you don't have any bias into your process. But if you want to really specify a specific process, let's say oil and gas process, okay, just as an example. You know, uh, if you say oil and gas, Aspen uh, just selects six property thermodynamic packages, Payne Robinson, Redlich Kwong, and others for you. But if you say my process is, let's say, a petrochemical process, you see your options are more. Yeah, some of them are even new. NRTA, Uniquac, and so you see. But if you say common, so it shows you the most common thermodynamic packages that are used in chemical industries. So you see, this is really important how you select your thermodynamic package in Aspen. If you say all, so then it's more difficult. You need to really spend time to understand what type of equipment you use. So anyway, I I I strongly believe that you should see what type of biomass conversion process you are using for your project, and see which of these industries are close to your biomass. For example, if it is gasification and combustion, in my opinion, for example, um, a power is okay. Okay, if you use the power, for example, you see you have these four options. But if in your system specifically, and you have, for example, you are producing syngas, okay, you can select the syn fuel. So you see, it gives you three options. So it helps you to identify your thermodynamic package. So these are component and methods, and there are other things that I will leave it to you to learn. But back to simulation, if you go to simulation menu, here is where your fun starts. Aspen has a lot of uh, simulation, kind of tools to really translate a real process to simulation interface in terms of mixers, in terms of separators, heat exchangers, columns. I mean, like a distillation column, extraction column, leaching, whatever. Reactors, there are different reactors, stoichiometric, yield, equilibrium, Gibbs, CSTR, polite flow, batch reactor, even more. Uh, Pressure changers, pipes, compressors, pumps, um, manipulators, solids. This is very important, especially if you have, since biomass, is a solid material. So if you want to do drawing, if you want to do, for example, filtration, if you want to do solid crushing or grinding, these kind of things are here. See, crushers, screens. Screens are like filters. Okay. What else? Granulator, classifiers, fluidized beds. It's very important if you want to design a fluidized in Aspen. I don't know why Aspen doesn't put fluidized bed reactors inside here, because fluidized beds are not necessarily reactors, because even we have dryers that are fluidized bed. So that's why, um, since fluidized bed are gas solid systems, Aspen considers the fluidized bed inside under the solids menu. Anyway, solids separators like cyclones, centrifugers, filters, hydrocyclones, electrostatic precipitator. This is very important. Electrostatic precipitators are unit of operations that are used in order to capture very fine particles or even very fine droplets like nano size or very a few micron liquid droplets, because otherwise they will accumulate in downstream and they make problems. People who work on gasification, for example, for the project, they have to really consider ESP. They are important unit operations. Anyway, my job here is not to teach you Aspen simulation, how it works. My job here was to show you that Aspen provides an assembly of various unit operations, reactors, separators, heat exchangers, utilities, and also helps you to define components, different sorts of thermodynamic package in order to have a very good simulation. In terms of, I forgot to say, in terms of streams, you can have materials, you can have energy or heat and work. So you see, but you need to really start learning Aspen. I'm sure uh, once you do one just case study with Aspen, your life will be very easy. You will learn everything with this simulation. So simulation Aspen is not about just what I showed you. These are equipment that exist. But the most important thing, as we discussed today, is how to use simulation. For what type of purposes you should employ Aspen Plus and or any other simulation, and to really save time and make money at the end. Because we are engineers and we want to, always solve a problem and make profits. So I really strong that again you really learn Aspen for this course. I'm not pushing you to 100% learn Aspen, but even if you learn about 40%, 50% of Aspen, believe me that you will benefit a lot in your future professional life. Okay, so it was about the course of today. I hope you got an idea about importance of process simulation. Let me stop the recording. If you have any question,